Um, Homework 14, I'm going to cut you a rare break and give you until 11:59 on Friday to submit that assignment. Of course, most of our assignments this semester have been due before class, but just because I know that it all comes pretty hot and heavy the last week of the semester, and also in case you learn something today that you need a little extra time to apply, I'll change the submission deadline for Homework 14 on Blackboard to be 11:59 on Friday. So the Friday after that is when we have our final exam, and our final is from 10:15 to 12:15, and you've been through it before. It's the same process we followed for our earlier tests, where the exam was distributed on Blackboard, and you could print it out and write your answers on the printed exam, or you can write it by hand, and just view the exam on the screen. If you do that, please use just plain paper. Don't use line notebook paper, don't use graph paper, don't do it like with light gray pencil on gray paper, which makes it hard to see. Scan the image to black and white with good lighting so that the contrast is good, so the image is in focus. I can't grade what I can't see. So please pay special mind to making your work easy to read. So the final exam format is going to be that it's open book, open note, use your previously solved in-class exercises, your previously solved homework assignments, but what you shouldn't do is access any website during the exam, and that includes YouTube. So you can't go back through a lecture when you should be focusing on the test. And the main reason I say that is, boy, that would just be a waste of time to be rewatching a lecture during the exam. And then the other thing is you shouldn't communicate with other people during the test. What you submit should be your work and what you figured out. So that's the parameters of the final exam. We'll just touch on the background of that one last time in our class meeting on Friday. Today we're going to be talking some more about cost estimation techniques coming from Chapter 15, and we're going to discuss specifically the idea of learning curves. But before we get into learning curves, are there any questions on the announcements or just the course in general that anybody would like to ask before we move on? All right. Here is a sweatshop. And if you've ever seen video of a sweatshop, maybe you were struck, like I was, by how quickly these people can sew. I had to take a home economics class in middle school, and we sewed a little pillow, like a decorative pillow, and I was so slow at that. We did 3 sides of the pillow with a sewing machine, and then the last side, if I remember correctly, we had to stitch it up by hand. But even with the sewing machine, I was just so clumsy and so inexperienced that I was sewing that seam very, very slowly. But if you've ever seen a video of someone who sews for a living, they may sew an inseam for pants in like 1 second. So just like zip, like through that entire length of fabric, and it's exactly in the right spot. And so it kind of is a perfect illustration of the fact that when people do things day in and day out, not only do they get skill at that, but they're able to identify shortcuts and little tricks of the trade that enable them to work more quickly and be more efficient. So that applies not only in garment production, but also in other things as well. And as an illustration of what a learning curve is, let's just define some terms. And let's say, for instance, that someone who's sewing a shirt was able to do that in 12 minutes the first time they sewed a shirt. So we're going to go through some terminology and look at a formula a little bit later. And so the first time you sew something, when you have 0 prior experience, we're going to call that K. So it's how much resources you use the first time you attempt a task. And so it may be time, but it could be other resources as well, besides time. But for this first illustration, let's just say that it's how much time you're consuming to sew a shirt. Now, this idea of a learning curve also applies in manufacturing. It applies to things like writing computer code, designing a building. Whatever you do, it's most likely that you're going to be better at it in subsequent times when you've had a little bit more experience and responsibility. Now here's kind of an interesting video that shows the effects of automation. Let me just pause this recording for a moment because I don't want to get in trouble. Okay, so we're going to watch Okay, so what you can see is that what they're doing in Amazon is they are using these little robots to bring the shelves to the people who pick the items out of the shelves. And so not only is it reducing how much space they need in the warehouse, because there don't need to be aisles that are big enough for people, they can have these shelves packed pretty closely together without any room in between, because the little robots are able to go under the stands that the shelving is on. But it's really increasing how quickly things can be done inside of this warehouse. And the robots optimize and get faster over time as well. They probably have a much quicker learning curve than a person, but machine learning allows the robots to become more efficient at their task. So these ideas of learning curves, I think, apply beyond just to human systems to other systems as well. All right, so remember in the first example, in this first illustration, we said K was how long it takes to do it the first time. Now, let's say that this person is installing an oil pan, and the 5th oil pan that they ever installed took 40 seconds to install. And then the 10th oil pan that they installed took 37 seconds. Now, the 5th to the 10th is just an example of where you've doubled your experience. So if you've done 10 oil pans, that means you have twice as much experience as you did when you had only installed 5 oil pans. So the same could be said of if you go from 1 to 2. You've doubled your experience when you've gone to 2 installed compared to when you'd only installed 1. And so, you know, obviously the same thing is true if you go from 2 to 4 or from 3 to 6. Anytime you double your productivity, double your experience. So this S variable that is going to be in the equation I show you, S refers to what is the ratio of resources consumed when you've doubled your experience. So from the 37 divided by 40 means 0.92. And so if that was 0.1, it means that you're not getting any better. But the lower this ratio, it means that you're still improving really quickly because you're using considerably less once you've doubled your experience. So this S ratio is just related to the doubling of experience. Now, here is a graphical representation of this curve equation that we're going to work with today. And a learning curve is a model, meaning just like a simplified representation of reality. And it takes into account increased efficiency and organizational improvements when people are repetitive and just iron out all of the kinks and get a process streamlined. It has other names besides learning curve. Sometimes it's called a manufacturing progress function or an experience curve. And we've already talked about some of these variables like K, for example, and S, which was the ratio of when you've doubled your experience. But the way that these fit into the equation is as shown on the bottom left. So you'd use this equation to try and predict how much of the input resource is required for a certain number of units. So U is a certain unit. Like how long is it going to take, for example, to sew your 20th shirt? So the way that you could predict the number of minutes required to sew your 20th shirt is you start off with K, which is how many minutes you took with the first shirt that you sewed. And you're assuming that you're not going to get worse at it over time, that it's going to be some percentage of that first time you made it. And so then U to the N is going to end up being some decimal that's less than 1, meaning like a percentage of that base first time you made the thing. And the way that U is determined is, u to the n is determined, is you take that s value that was the ratio where you're doubling your experience, take the log of that, divide by the log of 2, and that's the exponent, learning curve exponent n, that you use in this function. And then u itself is the number that you're trying to predict. And so remember I'd said if you're going to predict the 20th shirt that you've sewn, then it would be 20 to the power of some value n. So we're going to get some experience using this equation today. In this example, let me show you what you would do if you take 85 minutes to sew your first pair of pants, and the second pair of pants you take 76.5 minutes to sew it, and then with the fourth, 68.85. So with the data that we have, we're able to define S either with the first to the second, or it can be defined by going from the second to the fourth. And either one of those is going to work. And in fact, if you run the numbers on it, you're going to see that the ratio is the same. I kind of designed this example to be that way intentionally. So K equals 85. 85 minutes is K. And with your calculator, now we need to know what is S. And so if you've got your calculator handy, S would be either 76.5 divided by 85. So if you do 76.5 divided by 85, you'll see that S is 0.9. Or it could be 68.85 divided by 76.5. You'll get the same thing. You'll get that it's 0.9. Okay, so now we need to take the log of that. So the log of 0.9, I'm just doing it now on my calculator, the log of 0.9, and then divide that by the log of 2. So the log of 0.9 was negative 4.57, and then the log of 2 is 0.301, and you divide those two by each other and get negative 0.152. Now let me see if I have this scanned. Oh, there it is. You may even have this there in your slides potentially. So we got the ratio either from the first to the second or the second to the fourth, but S is the same either way. Took the log of it and calculate N. Now we want to know in this example how long will it take to sew your 10th pair of pants. And so U is 10. And so we're going to find the number of minutes required to sew the 10th pair of pants. So if U is 10, then it's 10 to the power of N, where we calculated N with this formula. And what you can see is that if 85 minutes was our base first try with no experience, now once we've made 10 pair of pants, then it's going to take us only 70% as long, approximately, because 0.704 means that after we've got 10 pair of pants of experience, then it's going to take us 70% as long. So 59.5 is how long it takes to sew your 10th pair of pants. Now, the other part of this question is saying, what's the total time required to sew 10 pair of pants? And so let me illustrate that with Excel, because you know me, I love Excel, and if there's an automated way to do something, then I'm absolutely going to show it to you. So let me just fire up Excel and then look at this together. Okay. So I'm going to have the pair number and then the time in minutes. And then I guess over here on the side, I'm going to define a couple of constants. So our first pair of pants took 85 minutes. We know that. The second pair of pants, let me make that a little bit bigger in case you can't quite see it. Okay, the second pair of pants we know took 76.5. Now, all the rest of these we can calculate based on the trend that is implied by this formula. But first of all, we need to have S. And do you remember, S is the ratio, and it's the smaller one in the the smaller value in the numerator divided by the larger value in the denominator. So that's S, and then N. N is log of S divided by log of 2. So equals log of S divided by log of 2. Okay. So for the rest of these, I'm just going to apply this function. So it's going to be the amount of minutes required to do the third pair of pants, the fourth pair of pants, the fifth pair of pants, and so on. Okay, so equals K, which is that first value, multiplied by U, which is whichever pair of pants we're on. So 3 to the power of N. And I need to anchor that reference to N so it's always looking there even when I drag my formula downward. Okay, so it says 71.9 minutes. And does that make sense? Kind of with the trend that we already know is the fourth pair of pants should take 68.85. So let's see if it does that right. Wow, it does. Great. 68.85 minutes for the fourth and the fifth. And now I can just double click down here and it will do it through all of them. And by the way, what had we manually calculated? In this previous slide we saw that, oh, it must be here, 59.9, and we got 59.9 for the 10th pair of pants. And so the last part of that problem says, what about all of them? The first 10 pair of pants, cumulative time spent would be the sum of all of those. So the first pair of pants, the second, and all of them. So it's going to be 679.5 minutes it will take to sew that first 10 pair of pants. And I think you can probably get a feel for why this would be so useful. This portion of our course is all about cost estimation. And if you're going to be predicting how much time it takes to build a building, or if you're going to be predicting how many of your people are going to need how many days to accomplish a certain project, then taking into account their improvements in efficiency will be critical. Okay, so here's today's in-class exercise. What I'd like you to do is practice using these same ideas, and here's the paper as you see it printed out. I would like you to solve this one by hand. You sometimes just get a feel for the equations a little bit better if you are working them out on paper. And so this one you ought to solve by hand, not with Excel. A Rubik's Cube. I'm really bad at a Rubik's Cube, but let's just use this hypothetical and let's assume it followed this perfect curve. Now, of course, it's not going to always follow a perfect curve. There's going to be variability in the data. And the real world never follows a model perfectly, but that doesn't mean the model is useless. I mean, it's just a simplified way of understanding what's going on and to do some calculations. So let's say that this is the data you've got. You know the second time you did it, how much time it took, 24 minutes to solve it. And the fourth time you do it, you know, and the 8th time you did it, but you forgot to measure yourself the very first time. And so you're not going to know K directly from observation, but what you can do is you can back calculate. So in the same way that you can go from 2 to 4 and 4 to 8 in a systematic way using that S ratio, you can also go backwards in time and synthesize your K value by estimating how much time it would have taken if the same trend continues backwards. So if it's the same S ratio that goes from 2 to 4, then that ratio will apply from 2 to 1. So in other words, I'm suggesting you should calculate S and then use S to determine K. That's just a little hint. All right, so let me pause for a second. I am going to put you into the breakout rooms, give you a chance to chat with your classmates. You know, we don't have too many more of those. If you haven't been vocal or social yet so far this semester, now's your final chance to really say hello. And just think, you don't have too many virtual classes left because we're going to be in person in the fall. So like, hallelujah that this whole semester and that this awful virtual learning experience is almost done. Let me put you into these breakout rooms, and as we always do, we'll come back together in about 10 minutes to look over the solution together. Okay, so you can calculate S by using the ratio of, in my case what I did was I did the ratio of the fourth to the second. You get 0.91 that way, and I double checked my data by doing the ratio of the eighth and the fourth, same 0.91. So you can calculate N with that and get negative 0.136. And now the way that we back calculate to find K is, remember what S is it's a ratio of a doubling in experience. And so in the same way that going from 2 units to 4 units completed is a doubling of experience, so you can say from the first to the second is a doubling of experience. And so S equals 24 divided by K. Or if we rearrange that algebraically, K is 24 divided by S. So the first time it would have taken 26.38 minutes if this trend followed and if we had measured it. So all of that substituted in. If we want to know the 100th time and find out how long it's going to take to solve that Rubik's Cube puzzle, then it'll be 14.09 minutes. Once we have gone through it 99 times before and now we solve it the 100th time, 14.09 minutes. And so that's the experience curve or the learning curve function. And with these ideas you'll be able to solve a little bit more from the homework assignment. So before we part ways for today, let's just take one last look at these announcements. Remember that your final homework assignment number 14 needs to be uploaded to Blackboard before 11:59 p.m. on Friday. And then our final exam will be the Friday after that. So I will see you next time. We'll have our last class meeting on Friday at our usual time, and we're going to talk about depreciation and taxes, both really important topics. So please be sure to be here on Friday. It'll be worth it. All right, that's it for today, everybody. Take care. Bye-bye.